Let's see the associative mapping. So in associative mapping, any block of main memory can be placed anywhere in the cache, right? It can be placed anywhere. So we are taking the same example, right? So we have four blocks in our cache memory, right? So our capital N is 4, right? Then we have 8 blocks in main memory, right? Now all blocks are empty now. 0, 1, 2, 3. All are empty, right? So suppose first I need to put block number 0. So that block will be placed in first empty block. It is 0. Now there is a tag. Now what is the use of tag here? In previous case, direct mapping, the use of tag is whether the correct block is present or not. That we want to check. Here also we want to check that correct block. But we are not performing any modular operation here. The block can be present in any block. In previous case, we are just checking particular tag, right? After modulo operation, right? If this is the block where I can put my main memory block, then I need to check this tag only. And using this tag, I can say whether that block is present or not. But in this case, right, the main memory block can be placed anywhere, right? So tag indicates whether the block that I want is present or not, right? So I need to check each and every tag for it, right? So that's why this block is 0 is placed here. So tag indicates 000 means it indicates which main memory block is present, right? So total 8 blocks are there. So how many bits are required to uniquely address each block? So 3 bits are required. 3 bits are required, right? So starting from 000 to 111, this is the last one, right? So tag value or tag bits will be 3 and each will indicate this block, right? Now let's see the next one, block number 2. So next empty block, this, right? So I can put here 0 and 2, tag bits 010, right? Then 7, so 111, so 7 is here. Then you can place any other and you can check. So now in this case, your physical address, remember physical address number of bits that will not be changed, but the division can be changed. So physical address, remember physical address deal with how many words are there in your main memory, and to address those words how many bits are required. So in our case, in our main memory, total 32 words were there. 32 words. Now to address these 32 words, we require 5 bits, right? So your physical address, that is 5 bits. Now your physical address, that is divided in this first tag and word offset, right? In previous case, what we had, tag, then catch block offset and your word offset, right? But here we have only tag and word offset. So in previous case, first using modulo operation, we were finding cache block, and then we were using tag, we were checking whether particular block is present or not. If that block is located, if that block is located, then in that block, which word, that is indicated by this word offset. So obviously in this case also we require word offset, because after locating block, we require which word, right? So word offset is also required, and that will be same, because word offset, right, can be calculated based on your block size, based on your block size, right? If your block size is 4 words, means in block you can put 4 words. So after locating this block to indicate which word, right, uniquely identify each word, you require 2 bits, 00, 01, 10, and 11. So 2 bits for word offset. Now we don't require cache block offset because we are not calculating or we are not performing any modulo operation. We can place anywhere in your cache block, right? So what we require in tag? Main memory block number, right? In this tag we have main memory block number. Okay. So in this case 2 bits. Why 2 bits? This is the reason. 3 bits for tag. This depends on how many blocks are in there in your main memory. So total 8 blocks are there. 2 raised to 3. So 3 bits for tag. Right. So this way the associative mapping is working. We are directly identifying using tag. So suppose I need to search for block number 2, block number 2 in cache memory. So what I need to do? From first from first block I need to check the tag. So 2 is 010. So from first tag I am checking 000 and I want to search 010. Matching? No. Right? Then 010. Matching? Yes. Right? So for each tag you require tag comparator, right? When we perform in parallel, right? This is a faster access, right? But you require more hardware because at each tag you require one tag comparator. In previous case, right, we are checking for particular tag. Okay. So same example that I have given in the previous video, that is in direct mapping. Say example you need to solve for associative mapping, right? So in main memory you have 502 words. In your cache memory you have 64 words. Your block size is 16 words, right? So you need to give the answer for this. How many bits for physical address? How many tag bits are required? How many bits are required for cache offset? So here we don't require that. How many bits are required for word offset, right? If main memory blocks are 16, 9, 26, 7 are present in cache memory, then show tag of each cache. So one by one, put this block in cache memory. Now you don't require modulo operation. And then check that the block is present or not, right? So that thing you need to now. Previous case we have seen the word 9 is present in cache memory or not, right? So for word number 9 the physical address is 01001. This is the physical address, right? For word number 9. Now divide it in this manner: tag and word offset. So first 3 bit for tags, 2 bit for word offset. Means if block is present, it will be in it will be 01, means 0 and 1 bit, one word, right? So tag is 010. So what I need to do? I need to start comparing this tag with these tags, right? First is 000. No, 010. Yes, it is there. It is there, right? So now the block which contains word number 9 is present in cache. Is present in cache, right? It is here. It is here. Okay, now 0 1 0, right? That is the block and it is present, and in that block it is 0 1 at this position, word number 9, right? So in this case we have 0 2 7, right? And we have checked whether the word number 9 is present or not. Now assume I need to put block number 4 into cache block. Then in the direct mapping, if I need to do this, I will perform modulo operation. 4 modulo 4, answer is 0. So I need to put in block number 0. Before that I need to replace this one. So I need to take out this and need to place 4. Though this block is empty, right? Though this block is empty, right? But now in associative mapping 0 is there. If I need to put block 4 into cache memory, then I will start searching whether there is any empty block, and I found that empty block. So I will place 4 here and the tag bit for 4 is 1 0, right? So this is associative mapping, and solve this example later on. We'll make video on this solution also. Now set associative mapping, right? So to overcome the limitation of associative mapping, we have a set associative mapping. So what is that? So advantage of direct mapping and associative mapping, that you can combine in set associative mapping. In associative mapping, we need to check each and every tag. We, in our example, we had only 4 block cache memory block, but assume that some larger cache, if you have 32 blocks or 64 blocks, then you need to search each and every block. For that you require hardware, right? So in set associative mapping, it is combination of direct mapping and associative mapping. So in that, after dividing your cache memory into blocks, right, the are blocks are grouped in set. Block are grouped in set, right? So based on that, it is said that k way set associative means in one set how many blocks are there. In one set how many blocks are there, right? If I say two-way set associative means in one set two blocks are there. One set, how many blocks are there? Two blocks are there, right? So first I need to find out how many sets will be there in your cache memory, right? So easy. How many blocks are in cache, and per set how many blocks? So capital N is total block in cache, and K is how many blocks per set, right? So you will get the how many sets will be in your cache. Now, how to place the block from main memory to cache memory. So jth block of main memory has to be placed in jth mode S. Now this is S based on how many sets, right? So modulo operation we are performing on set. In direct mapping, we were performing on n, right? Blocks of cache. But now we are performing on set, right? So this way, you will find out which set. This way you will find out which set. And within the set, it can be placed anywhere. Within the set, it can be placed anywhere. So in direct mapping, we were fixing direct block. In associative mapping, all blocks are open. But now in set associative mapping, we have grouped the blocks in set. So now what we are doing? Using modulo operation, we were telling that you need to go in this set, but in that set you can be placed anywhere, right? So this is the combination of direct mapping and associative mapping, right? So it will take the advantage of direct mapping and associative mapping. Let's see the example two-way set associative mapping. So first, how many sets? So in our example, in cache memory, 4 blocks are there, and two-way set associative means 2 blocks per set. So how many such sets can be formed? Two, right? 4 blocks, right? Cache memory. So number of blocks are 4. Now two sets, right? So main memory we know how many blocks? 8 blocks. Now there are two sets, one set and second set. So 0 and 1 block that is combined, and 2 and 3 that is also group, not combined, group. Okay. Then I want to put block number 0 of main memory into cache memory. So now I need to perform modulo operation. So in previous case we were performing modulo on number of blocks. So here it was 4. Now on set. So how many set? 2. 2. So 0 modulo 2 means 0. So this block 0 that can be placed in set 0. This is set 0 and this is set 1. So block 0 can be placed or need to be placed in set 0, and in set 0 it can be placed anywhere, right? Whichever block is empty, right? So let's put into block 0. Let's put into block 0, right? So here it is number 0. Next, 2. 2 modulo 2. Answer is 0. So 2 can be placed in 0. 2 can be placed in 0, right? But in set 0 it can be placed anywhere. So next empty is this one. This will be placed here. Got it? Then next is 7. 7 modulo 2. Answer is 1. This give you set. In which set this block you need to put. So 7, 7 modulo 2, 1. So it can be placed in set 1. I mean set 1, whichever block is empty. So this is empty. You can put here 7. Right? Then next, if it is a 4, then 4 modulo 2. Answer is 0. Answer is 0. So you need to put set 0. Is there any empty block? No. In that case, you need to take out one block and then you can put 4. If 2 was not here and 4 wants to come, then you can place 4 here and this will be changed. Now in this case, as I said, the number of bits in physical address will not be changed, but the division will be changed, right? So physical address will be divided in 3 parts. Like now it's set, offset, and then word offset. In previous case, it was tag and word offset in associative mapping. In direct mapping, tag, catch block offset, and word offset, right? So using set offset, it will identify which set, and then using tag, it will identify which tag. Okay, it will compare all the tags in that particular set, right? So 2 bits on word offset, as this will depend on catch block size in terms of word. So we have 4 words in one block, right? 4 2 to the power 2. So 2 bit. Set offset, right? 1 bit, as we have 2 sets, right? So to differentiate these 2 sets, we require 1 bit and remaining 2 bits for tag. Total 5 bits. Why? 32 words are there, right? To differentiate 32 words, 2 raised to 5, 5 bits are required. Now, try for word number 9 again. 0, 1, 0, 0, 1. Divide like this: 2 bits, 1 bit, 2 bits, 2 bit, and 2. So set offset. In which set? Set 0. So set 0. This one. In that set, what should be the tag? 0, 1. So from first block in that set, I need to start comparing. 0, 0. No. 0, 1. Yes. Means the word number 9, right? The blocks that contain word number 9 is present here in this block, cache block 1, right? Now the block is located in that block. Which word? So at this location. Okay. So instead of comparing with each and every tag of all the cache block, we have restricted it to set, right? So this gives you advantage of direct mapping and set associative. Okay. Now the same example, right? Just I need to mention two-way set associative and same physical address. This will remain same as it is. How many tag bits are required? This will be changed. Now it's a set offset instead of cache block offset. Word offset will remain same, right? As we have not changed the block size. Again, put this cache blocks, and then you need to check whether this word is present or not. Okay. Now take this one question. Consider 1 MB cache and 4 GB of main memory. This is 1 MB, your main memory or physical memory, that is 4 GB, partitioned into 64 KB blocks. So block size is given 64 KB blocks. So using this information, what you can find out? You can find out how many blocks are in cache and how many blocks are in main memory. This you can calculate, right? Hmm. How many bits are required for physical address if word size is 1 byte? Physical address, right? So physical address deals with your main memory, and you need to check how many words are there in your main memory, and based on that you can find out physical address, right? How many blocks are there in main memory and cache memory? So you can easily calculate. How many tag bits are required for direct mapping, associative mapping, and 8 associative mapping? So this thing, and one more question: how many tag memory in bytes are required for each cache, each case, right? Because you need to store the tag, right? So how many bytes are required? This thing you need to answer, and we'll see the solution for each and every case in next video. Thank you.